And we assume that there are at least two of them. Also, we have a set of voters, call it N. And again, we assume that there are at least two of them. And for both of these sets, we assume that they're finite. Furthermore, we endow all these voters with preferences, and we assume that every voter has a preference ordering over these sets of candidates. And by ordering, I mean a reflexive, complete, intransitive relation. We do not assume antisymmetry. That is, these rankings do not have to be strict, and that doesn't create any, allowing for indifference in our context doesn't create any problems, because rules such as the majority rule can easily accommodate indifferences because they wash out anyway. Right? If you count the number of people who prefer one alternative to the second and the number of people who prefer the second to the first, if you include in this count those who are different, they disappear on each side of the inequality. So that doesn't, again, in the presence of indifference doesn't create any problems. For most of our examples, we will use antisymmetric relations simply because they will be easier to deal with. That's all. But we don't need this assumption at all. So we use Ri in script R to denote an ordering on X of voter I. And again, by an ordering, I mean a reflexive, complete, and transitive relation. So script R is the set of all orderings. We are not making any domain assumptions here. We allow voters to have any preferences they may want to express. A profile then is an n tuple. N is the number of voters of these relations. Bold R. And of course, it will be an element of the n-fold Cartesian product of the set of all orderings. Now the object of interest is a voting rule, and the voting rule assigns selected candidates to profiles. Right? Give me a profile, and the voting rule spits out the candidates that are being selected for this profile. So we can do this in terms of voting rule, or more generally, a sort of choice correspondence. And the voting rule is just a mapping F that has as its domain the set of all possible profiles times the set of all possible feasible sets that we may encounter, the set of all possible agendas from which we may want to choose, and that is the set of all non-empty subsets of our set of candidates. It maps to this set of non-empty subsets of candidates, and in order to be well defined, it has to be such that we can only choose something that's actually feasible, so that F applied to a profile R in the feasible set S has to be contained in S. For all S in this. Right? Very standard. Now, Condorcet's proposal is to identify, to check whether there is a candidate who is a Condorcet winner in the sense that this candidate beats everyone else in a pairwise comparison. So candidate X is a strong Condorcet winner. Strictly speaking, I would have to say a strong Condorcet winner for a given profile in a feasible set, but I'll skip this just to move ahead a little more quickly. If, well, again, if X beats everyone else. That is, if the number of voters, I in N, who prefer X to Y, so PI is just a strict part of I's preference relation, is greater than the number of voters who prefer Y to X, and that has to be true for all Y different from X. Right? That's what we call the strong Condorcet winner. And again, there's a case to be made. If there is such a strong Condorcet winner, this candidate should be elected. And you don't have to do anything else. You don't have to look any further. Now, analogously, strong Condorcet loser is a candidate who loses against everyone else. So you just reverse the inequality. Now, the strong Condorcet winner principle, or strong Condorcet winner consistency, as the property is often referred to. Basically, it says it's a requirement imposed on a voting rule that says if there is a strong Condorcet winner, then this candidate should be elected and we're done. I use a singular strong Condorcet winner because clearly there can only be one, right? The set of strong Condorcet winners is either empty, if there is no such candidate, or it contains at most one element, because you cannot have both of these for more than one candidate. So, in any combination of a profile and a feasible set in our domain, I don't write it out again because I guess it's understood again. If there is ever any ambiguity, just let me know. So if there exists a Condorcet winner, well, let's give it a name. Let's just SCW of R and S is the set of strong Condorcet winners. And again, this set is either empty or a singleton. So if this set is non-empty, strong Condorcet winner consistency demands that what we choose should be from this set. Choice that we make from this feasible set for this profile will be contained in the set of strong Condorcet winners. And of course, it would be equivalent to say that this is equality because this has only one element. Therefore, this is not empty. So if it's contained, it has to contain the entire set. Analogously, strong Condorcet loser consistency goes in the other direction. It says if there is a strong Condorcet loser, again, there can be at most one. This candidate should never be elected. So strong Condorcet loser consistency says for all combinations of profile and a feasible set, the intersection of the set of candidates that is chosen and the set of strong Condorcet losers should always be empty. Again, I use strong Condorcet loser R net for the set of strong Condorcet losers. Again, so far so good. These properties are fairly uncontroversial. The only potential problem with them is that in many situations, Condorcet winners and losers may not exist. Now, one possible remedy is to replace strict inequalities with weak inequalities. If you want to have weak Condorcet winners or losers, you just replace these inequalities with their weak counterparts. Right? And you get sets of weak Condorcet winners and weak Condorcet losers. The problem with defining consistency properties analogous to strong Condorcet winner consistency and strong Condorcet loser consistency is it's inconsistent because an alternative can be a weak Condorcet winner and a weak Condorcet loser at the same time. And that can happen not only in degenerate situations. I mean, one obvious degenerate situation where this happens is if each voter's preference is universally different, then clearly everybody's a Condorcet winner, everybody's a Condorcet loser. But it can happen under much more restrictive circumstances. Just to give you an example, suppose we have lights don't work here? Or